Let me start by thanking the organizers for inviting me to speak here. It's always a pleasure to be back in Berlin. The title of my talk is Form Factors in N=4 Super Yang-Mills Theory and Beyond. I should mention here that in contrast to everybody else today, I'm speaking about the form factors in the four-dimensional theory, not the two-dimensional one. As my title suggests, I'm first going to give you an overview about form factors in N=4 Super Yang-Mills theory, reviewing some recent developments during the last 2 years, as well as mentioning ongoing work. I'm then going to talk about a curious connection between the dilatation operator and the scattering matrix, which is valid in any theory. This latter statement is based on some joint work with Simon Caron-Yot, which appeared last month on the archive. So let's see whether this works. No? Okay. So that was basically already the structure of my talk. Let me start by giving you a motivation and introduction to form factors. One quantity that has been well studied in N=4 Super Yang-Mills theory, but in fact in any quantum field theory, is the scattering amplitudes of elementary particles. A scattering amplitude is defined as the overlap of an n-particle outgoing on-shell state with a vacuum. During the last 1.5 decades, scattering amplitudes have been very successfully studied due to the advent of the so-called on-shell methods, but recently also due to integrability. Another very important quantity in a conformal field theory like N=4 Super Yang-Mills theory is the correlation function of gauge-invariant local composite operators. A correlation function is defined by taking products of these operators O at positions xi and wedging the result between two vacua. During the last 1.5 decades, correlation functions have been very successfully studied via integrability in the case of two-point functions, but recently also for three-point functions, as everybody else today has been telling you. The form factor of a gauge-invariant local composite operator O is defined as the overlap of a state created by O of x from the vacuum with an n-particle outgoing on-shell state. As such, form factors form a bridge between the fully on-shell scattering amplitudes and the fully off-shell correlation functions, whose momenta after a Fourier transformation satisfy no mass shell condition. Form factors in N=4 have been first studied 31 years ago by van Nerven. In recent years, there has been increased interest both at strong as well as at weak coupling, with authors now ranging from A to Z. In this talk, I will look at weak coupling. Let me start by introducing some notation. In order to apply the powerful on-shell methods that were developed for the study of scattering amplitude, we first go to momentum space. We take a Fourier transformation to exchange the position x of the operator for a momentum q, which is off-shell as it does not square to 0. Next, we use spinor helicity variables to parameterize the on-shell momenta pi as lambda, lambda tilde. Using Nair's N=4 on-shell superfield, we can moreover package all different component form factors into one super form factor. Finally, we can split off the dependence on the gauge group generators T by defining color-ordered form factors in complete analogy to the amplitude case. The only difference to the amplitude case is that the operator's momentum q does not partake in the color ordering, as the operator is a color singlet. Now let me give you an overview about form factors in n equals 4 super-Yang-Mills theory, starting with some simple form factors at tree level, then going to form factors of more general operators and to loop level. The simplest scattering amplitude, I guess all of you have by now seen, is the MHV tree level amplitude given by the Park-Taylor formula. In a convention where all particles are outgoing, this describes the decay of the vacuum into 2 minus helicity gluons at positions I and j, as well as n minus 2 plus helicity gluons at all other positions. The simplest form factor, MHV and tree level again, describes the decay of an operator trace of phi squared into 2 scalars at positions I and j and n minus 2 plus helicity gluons at all other positions. It looks almost identical to the Park-Taylor formula. The only difference is the power in the exponent here, which is 2 instead of 4, and the operator's momentum q, which appears in the momentum conserving delta function. This operator, trace of phi squared, is the lowest component in the protected stress tensor supermultiplet, which has also been mentioned previously in this conference. One fascinating on-shell method that was developed for scattering amplitudes are on-shell diagrams. It was shown in particular by Niemer and friends that the tree-level scattering amplitudes in n equals 4 super-Yang-Mills theory can be described of diagrams which are built using only 2 building blocks. Those building blocks are the tree-level 3-point MHV amplitude, which is depicted as a black vertex, and the tree-level 3-point MHV bar amplitude, which is depicted as a white vertex. For form factors of the stress tensor supermultiplet, we have found a similar situation. There, tree-level form factors can also be characterized via on-shell diagrams, which need only 1 further building block in addition to the black and the white vertex. This further building block is the 2-point tree-level form factor of the stress tensor supermultiplet, which we depict by a double-line vertex. For amplitudes, it was moreover found that all tree-level n-point n to the k MHV amplitudes can be given as residues of a certain integral over the Grassmannian k, n. Here, the Grassmannian is the manifold of all k-dimensional planes in n-dimensional space, and Niemer has briefly reviewed this also in his talk. For form factors, we found a similar construction. Also here, we can find the tree-level form factors as residues of a certain Grassmannian integral. But now the Grassmannian is k, n plus 2, as we're using 2 on-shell momenta to parameterize the off-shell momentum q of the operator. A further interesting technique that can be used for form factors is, of course, the connected prescription, which Song-Hee has briefly mentioned in his talk, and this is connected to the Grassmannian formulation. A further interesting question to answer for form factors concerns their symmetry. As I guess all of you know by now, amplitudes are Youngin invariant. This can be rephrased in terms of an eigenvalue equation for the monodromy matrix M. This means M acting on the amplitude is proportional to the identity matrix acting on the amplitude. Thus, form factors and their spectral or central charge deformations can be found as solutions to this eigenvalue equation via the integrability-based technique of R operators. For form factors of the stress tensor supermultiplet, we have again found a similar situation. Those form factors are no eigenstates of the monodromy matrix. However, they are eigenstates of the transfer matrix that is given by taking the supertrace of the monodromy matrix. Thus, they and their central charge or spectral deformations can also be constructed as solutions now to this eigenvalue equation. Moreover, this property generalizes to minimal tree-level form factors and leading singularities of general composite operators. It implies a tower of conserved charges and symmetry under a part of the Yangian. Let us now come to general operators, and we'll construct those using twistor space. In the planar limit and at tree level, it is sufficient to look at single trace operators. A single traced operator is built by taking the product and then the trace of L fields that are irreducible. That means they are transforming in the irreducible singleton representation of PSU 2,2/4. These fields are the scalars phi, the fermions and antifermions psi and psi bar, as well as the self-dual and anti-self-dual part of the field strength. Moreover, we can have these covariant derivatives acting on the different fields in such a way that all the SU2 indices alpha and SU2 bar indices alpha dot are completely symmetrized. In order to perform the symmetrization, we can contract the open indices with superpolarization vectors that are light-like, and then we can recover the indices by taking derivatives with respect to the components of these superpolarization vectors. One advantage of the twistor action of n=4 super Yang-Mills theory is that it repackages the interactions of the theory in a more economic way. In particular, n to the k MHV amplitudes are given in terms of diagrams at tree level that contain exactly k+1 vertices and k propagators. And the same is true for form factors. In particular, MHV amplitudes and MHV form factors are immediately given by inserting momentum eigenstates into the corresponding vertices. For this, however, we need the vertices of the operators in twistor space, which are not just given by these expressions as in usual space-time. Our solution to this problem is to construct the operator vertices by taking derivatives of a polygonal light-like super Wilson loop in twistor space and shrinking this to a point. The details of the construction are a bit technical, so let me tell you about the idea behind the construction instead. It is based on recalling that the field strength is the curvature of the gauge connection. And as we've all learned in general relativity, we can compute the curvature of a connection by parallel propagating around a parallelogram, then taking derivatives and setting the size of this parallelogram to 0. In n=4, all fields transform in the same supermultiplet as the field strength, so we can obtain the vertices for all fields this way. And if you're interested in the details of this construction, you've still one more day to visit our poster on this. Now, inserting the momentum eigenstates into these vertices, we obtain the MHV form factor for a general operator. As expected, it contains a momentum-conserving delta function and a Park-Taylor denominator. All fields in this composite operator do have a certain SU2 bar charge and a certain SU4 charge. These charges have to be distributed among the external fields. This first sum over the B's is on the external fields on which these charges land, and the second sum here and the third line account for the combinatorics. In particular, for chiral operators, this factor here will just be a multinomial coefficient. The angular brackets in the second line are now simply determined by little group scaling and color ordering. Note that this result is new, but if we restrict ourselves to certain subsectors like the SL2 or SU2 sector, we find a match with the results previously available in the literature. Moreover, we've checked this in certain representative cases using Feynman diagrams. Later, our result was also confirmed using the Lorentz harmonic chiral superspace. That concludes what I wanted to say about tree-level form factors. Let us now go to loop corrections. And for the sake of simplicity, we start with loop corrections to minimal form factors. That means we have as many external fields n as fields in the operator L. As for amplitudes, we can expand the loop corrections in the effective planar loop coupling G tilde squared. In contrast to amplitudes, however, the loop correction I is not a simple number, as the operators do in general not renormalize diagonally. Instead, this is an operator which acts on the minimal tree-level form factor. As for amplitudes, we can, however, take the logarithm of this operator. It contains some universal infrared divergences which are governed by the cusp and the collinear anomalous dimensions. In contrast to amplitudes, however, this logarithm also contains an operator-valued ultraviolet divergence, which is proportional to the dilatation operator. Hence, we can simply compute I via on-shell methods and read off the dilatation operator from the logarithm. This has by now been worked out in quite a number of examples. At one loop order, using generalized unitarity and an integrable basis which is available there, I've calculated the complete one-loop dilatation operator of n equals 4 super Yang-Mills theory this way. This is the first derivation of the complete one-loop dilatation operator using field theory alone, before it was obtained, of course, by symmetry. In particular, this derivation also constitutes a field theoretic derivation of a connection between the one-loop dilatation operator and the 4-point amplitude, which was previously derived by Benjamin Zwiebel using symmetries, and which originally goes back to Niklas Beiset. At two-loop order, we have also shown how to obtain the Konishi anomalous dimension and the SU2 dilatation operator this way. Note that in the former case, evanescent operators play an important but subtle role. Recently, the Green-Merry group has also used this to obtain the mixing matrix of classical dimension 3 operators in the SU2/3 sector. And in an upcoming publication, we will show how this works for operators with finite Magnum numbers in the SL2 sector. Alternatively, we can also use on-shell methods to compute correlation functions and obtain the dilatation operator this way. But having used both approaches with unitarity for the two-loop Konishi anomalous dimension, we found that form factors are more efficient. Instead of the divergent terms in the logarithms, we can also look at the finite terms, or rather at the BDS remainder. The BDS remainder is defined as the logarithm of the renormalized interaction, hence the REN, minus the expectation from the universality and exponentiation of the IR divergences. For amplitudes, the BDS remainder famously vanishes for 4 and 5 points, but is non-vanishing for higher points. In particular, the symbol has been proven to be very powerful in simplifying the remainder. For 3.2 loop form factors of the stress tensor supermultiplet, it was found that the remainder has uniform maximal transcendentality, as in the case of amplitudes. Moreover, it matches the highest transcendental part of the Higgs to 3 gluon remainder in QCD. Looking at minimal two-loop form factors of general non-protected operators, we have found that their remainders are of mixed transcendentality. However, the highest transcendental part is universal and matches the remainder of the BPS vacuum. We've originally observed this in the SU2 sector and conjectured it to be true in general. Further support for this conjecture has thence been found in the SU2/3 sector by the Green-Merry group and in the SL2 sector in upcoming work by us. That concludes what I wanted to say about form factors in n=4 super Yang-Mills theory. Let us now go beyond n=4. If you've been lost in the first half of the talk, now is also a good time to reconnect, as the second half won't build on the first one. Our aim is to calculate renormalization group coefficients, such as anomalous dimensions and beta functions, via on-shell methods, but now in any theory. This is, of course, related and in some sense a generalization of the developments in n=4 I've presented before. Moreover, on-shell methods were also used by Akani Hamed, Casazzo, and Kaplan to compute the one-loop beta function as a sum of bubble coefficients plus collinear data. Similar ideas were also used to explain certain vanishing matrix elements in the mixing matrix of dimension 6 operators in the standard model effective field theory. Let us begin with some very general considerations at finite coupling. We consider a form factor, f, now in a plane font, and rescale all momenta by a common phase alpha. This rescaling is given by the dilatation operator, which is the sum of pi mu del by del pi mu. Due to Feynman's I epsilon prescription, form factors are not real, but slightly imaginary. If we now look in the complex P0 plane, we find that a rotation by pi brings us to the wrong side of the branch cut. We arrive at the complex conjugate form factor f star, which is the form factor computed using anti-time ordered propagators. Thus, analyticity tells us that the form factor is equal to e to the I pi dilatation operator acting on the complex conjugate form factor. The second important ingredient in our considerations is unitarity. For the S matrix, unitarity tells us that S dagger is equal to 1. Or writing the S matrix as 1 plus IM, we find that the discontinuity of M is related to M dagger. Formally, form factors can be considered as small perturbations to the S matrix, where we now use curly font F to denote form factors which have non-vanishing initial as well as final states. Then unitarity tells us that F is equal to S F dagger S. If we restrict this to the usual situation where the initial state is the vacuum, this equation reduces to F equals S F star. Now, if we combine the statements of analyticity and unitarity, we find that the dilatation operator is minus the phase of the S matrix divided by pi. And this is the main result of the second part of my talk. From the renormalization group equations, we know that the action of the dilatation operator on a form factor is given in terms of the ultraviolet and infrared anomalous dimensions as well as the beta function. So we can obtain these quantities from the S matrix. I should also mention that we are strictly speaking omitting CPT transformation in this equation, as Amit has kindly pointed out to us. Now let us apply this general equation to several concrete examples. The first example is the one-loop beta function in QCD, or rather in pure Yang-Mills theory. We now consider the general equation for the two-point form factor of the Lagrangian, which is proportional to f squared. At one loop order, the beta function contribution drops out, and we can obtain the universal infrared anomalous dimension from the requirement that the stress tensor T is protected. The product of the S matrix and the form factor is simply given by this two-particle phase space integral, and in order to parameterize it, we use a rotation of the spinor helicity variables lambda, which was already given in Zwiebel's work. Now let us look at the ingredients here, the S matrix or M and the two-point form factor. The two-point form factor of the Lagrangian, as well as its rotated version, is simply proportional to the angular bracket 1, 2 squared. The four-particle scattering amplitude is simply given by the Park-Taylor formula. For a pair of color singlet minus helicity gluons, it looks like this. If we now insert the explicit parametrization of the phase space integral, this ratio of angular brackets just reduces to 1 divided by cos squared sine squared. If we now insert this in the previous equation, we find that this phase space integral reduces to a simple integral of trigonometric functions. Here, this is just this factor, and the second factor stems from the IR subtraction, which we perform via the stress tensor. Together, these give a convergent integral, and thus a finite result for the one-loop anomalous dimension of the Lagrangian. The anomalous dimension of the Lagrangian is related to the beta function by taking a derivative. So we obtain the famous result for the one-loop beta function of Yang-Mills theory, which is proportional to minus 11/3. Moreover, we find that this beta function is negative as the anomalous dimension is negative, and recall the anomalous dimension is minus the phase of the S matrix by pi, so it is negative because the scattering matrix here is positive, which is the statement that two gluons do attract. Basically, the same calculation also works for QCD with an arbitrary matter content, and here the matter content enters via the IR subtraction through the stress tensor. A second application of this general insight is that to twist two operators, and for the sake of simplicity, we'll start considering scalar twist two operators. That means we look at operators phi bar, m derivatives phi. In order to remove total derivatives which correspond to descendant operators, we take the forward limit p2 equals minus p1. then the minimal form factor just reduces to a monomial in P1. If we now insert this explicit parameterization of the phase space integral, we find that the rotated momentum is proportional to the unrotated momentum, and the proportionality factor is just this combination of trigonometric functions. Now, if you look into a table or book on special integrals, you will find that the azimuthal phi integral of this combination to the power m is just the mth Legendre polynomial. Now, inserting this into the phase space integral and performing the second integration, we find that the difference of the UV and the R anomalous dimensions is just minus AM divided by pi. Here AM is just the phase of the mth partial wave amplitude. So that is a very concrete special case of our general statement that the dilatation operator is minus the phase of the S matrix divided by pi. Now we can look at two very concrete examples. The first is that of twist 2 operators in the SL2 sector of n equals 4 super Yang-Mills theory. Inserting the explicit expression for the amplitude, we find that this integral reduces to the integral of the mth Legendre polynomial of cos minus the mth Legendre polynomial of 1. And here the 1 stems from the IR subtraction via the stress tensor. Now, this integral is proportional to the mth harmonic number, which is, of course, the well-known result. In pure Yang-Mills theory, we can now look at twist 2 operators, which are built from two gluons, and transform in the vector-like representation of the Lorentz group m halves, m halves. In spinor helicity variables, the minimal form factor just looks like this. As you know, gluons have spin, so the partial wave amplitudes look a bit more complicated, but nevertheless we can perform the calculation, and we've checked that we recover the moments of the DGLAP pattern evolution equation for the gluons. The third interesting application for this is actually a new one. In gauge theories, the one-loop infrared divergences are in fact universal, and they have this form. Now, using this, we can write down a formula for the complete one-loop dilatation operator in any gauge theory in terms of the 4-particle tree-level amplitude and the collinear anomalous dimensions. These can also be, of course, obtained from the 4-particle scattering amplitude via the stress tensor. So if you're studying a new theory and you're wondering whether this theory is one-loop integrable, you can now simply compute those tree-level 4-point amplitudes and check via our formula for the dilatation operator. In order to illustrate some features which generically occur at higher loop orders, we look at Yukawa theory with one real scalar phi and one wild fermion psi. The interaction part of the Lagrangian is given by the phi to the 4th term and the Yukawa term, which are described in terms of corresponding composite operators. Although these operators have a different number of fields, 3 and 4, so a different length, they do mix under renormalization. The mixing matrix has diagonal elements YY and lambda lambda, as well as off-diagonal elements Y lambda and lambda Y. As in the case of Yang-Mills theory, the anomalous dimension matrix elements are moreover connected two derivatives of the beta functions. At one loop, we can calculate the diagonal elements using the by now standard procedure from the 2-to-2 tree-level scattering amplitudes, where we use the stress tensor to subtract the IR divergences. The lower diagonal element in this mixing matrix decreases the length of the operator from 4 to 3, so it vanishes at one loop order. The first non-vanishing contribution is at two loop order and given by the 3-to-2 scattering amplitude at tree level. It can be written as cut of these two Feynman integrals, and we can parameterize the occurring 3-particle phase space in the 2-particle channel using this parameterization, which was also given in Zwiebel's work. The upper diagonal element increases the length from 3 to 4 and requires the non-minimal form factors with the 2-to-2 scattering amplitude as well as the 2-to-3 scattering amplitude. We can parameterize these phase space integrals using a modification of the previously used spinor rotations. And then we can perform the azimuthal phi integration via residue theorems. It is interesting that this one-loop calculation is in fact more difficult than the previous two-loop calculation. This is because each of the different channels, which can be written in terms of cuts of Feynman integrals, contributes a logarithm. Although the sum of these three terms is just a rational function, just 2 here in this example. This cancellation of the logarithms is a generic feature at two-loop order, and in order to push this completely to two-loop and higher orders, it would be extremely helpful to make this cancellation manifest or make each step of the calculation manifestly rational. Let me now summarize our results on Yukawa theory. From the aforementioned calculations, we obtain this mixing matrix. As in Yukawa theory, the derivative of the beta function are just equal to those mixing matrix elements, and from them we obtain the one-loop beta functions shown here, which are well known, as well as some contributions at two-loop order. Note that this system is very constrained. So, for example, this 4 y squared lambda can be obtained from this 4y squared in gamma lambda lambda, but it can also be obtained from this 8 y lambda in gamma y lambda. So there's some non-trivial consistency condition between the different matrix elements of the scattering matrix. Finally, let me comment on masses. So far, we have used the massless S matrix. This is in line with the usual application of renormalization group equations, where particles are either light, such that the mass is negligible, or they are heavy and we integrate them out. Moreover, the unitarity method correctly accounts for the running of the mass operators. Another property in massive theories is that we can obtain momentum-independent logarithms mu squared by m squared. These stem, for example, from massive tadpole integrals. These logarithms do have no imaginary part, and hence we cannot detect them via unitarity. Does that mean the unitarity method is incomplete? We would argue no. The renormalization group answers two distinct questions. The first question concerns the optimal Baire coupling at a given cutoff. This question is, for example, relevant for practitioners of lattice calculations, as well as for a possible UV completion of the standard model. And for this question, you do, of course, need the momentum-independent logarithms. The second question is more of a concern for collider physics. It addresses the question for the optimal running couplings to minimize large logarithms in physical observables such as cross-sections at a given energy scale. As momentum-independent logarithms do not depend on the energy scale, the momentum-independent logarithms are irrelevant for the second question. So we find that unitarity correctly answers question number 2. Let me now come to a conclusion. During the first half of this talk, I have shown you how many modern techniques from the study of scattering amplitudes in n equals 4 can be applied to form factors in n equals 4. These include on-shell diagrams, Grassmannian integrals, integrability at weak coupling, the twistor action, unitarity and generalized unitarity, as well as the application of the symbol to remainder functions, which show some universality. This has led to some increased understanding of form factors in n equals 4 superhang-Mills theory, as well as to some on-shell approaches to the dilatation operator. In the second half of this talk, I have demonstrated that in any theory, the dilatation operator is minus the phase of the S matrix divided by pi. Thus, we can obtain renormalization group equations like beta functions and anomalous dimensions from the S matrix. I've shown you how this works in several concrete applications. I've shown you how to get the one-loop beta function in QCD this way, the one-loop anomalous dimensions of twist 2 operators. And moreover, I've applied this to obtain the complete one-loop dilatation operator in any 4-dimensional gauge theory, a new result. Then I went on to illustrate some generic features that occur at higher loop orders in Yukawa theory. Of course, there's much more to be done in n equals 4 to push the knowledge of form factors to the current states of amplitudes. Possible interesting extensions include a form factor hedron as a counterpart to the amplitude-hedron, a bootstrap program for the remainder function of form factors, the use of integrability at finite coupling, etc. Both in n equals 4 and for general theories, it would be interesting to extend the methods I've shown you in the second half of this talk to full 2-loop order and obtain the complete 2-loop dilatation operator this way. One result which we got, which I hope to be of particular interest to this audience, is the complete one-loop dilatation operator in any theory. So if you're studying a new theory and you're wondering whether it is one-loop integrable, you can now just compute the 4-point tree-level scattering amplitudes in this theory, plug it into our formula, and check with the dilatation operator. Although our explicit expression for the dilatation operator is in 4 dimensions, as we're using the spinor helicity variables and the parameterization given by Zwiebel, our explicit result is 4-dimensional, but the general considerations leading to it are independent of the deformation of the dimension, so it should be possible and quite easy, I hope, to extend this to general dimensions 3, 2, for example. An interesting question then is which properties of this four-dimensional 4-point amplitude do make the one-loop dilatation operator integrable. We hope that this will lead to some new field-theoretic understanding of integrability, to the discovery of new integrable theories, and perhaps even to a classification of all one-loop integrable theories. Of course, there's much more to be done, but at this point, let me stop and thank you very much for your attention.
Thank you very much for the nice talk. The question was not scheme dependence. In theories for the coupling grants, physical dilatation variable is scheme dependent. How does it appear from your conception?
So we are, in a way, fixing this scheme by looking at the form factors. So the form factors are given in a particular scheme. They have a particular discontinuity, so that fixes that.
Are there any other questions?
Do you think is there any way to relate this to scattering up to the rotation operator without referring to the Lagrangian?
Sorry, could you repeat the question?
Is there any relation, or do you expect any relation to relate the rotation operator amplitude to scattering amplitudes without referring to the Lagrangian?
We are not referring to the Lagrangian here.
But again, you said one loop means you have some Lagrangian to conservation.
So what's, I guess, definitely not referring to Lagrangian is the general consideration at finite coupling. So these considerations are not referring to Lagrangian. And so also this general equation does not refer to Lagrangian. And this was also the motivation. As you know, there's a huge movement of going away from the Lagrangian and basically computing scattering amplitudes from anything but the Lagrangian. So one thing which is, of course, important to mention here is that we are making a statement about the dilatation operator and the scattering matrix. And in general, this is a matrix. So starting from two-loop order, we are also talking about the phase of the matrix and not about the phase of the 2-2-2 matrix element. So that's important to keep in mind if you're wanting to apply this to two-loop order. But yeah, this is not referring to a Lagrangian.
Are you accepting this four-dimensional sense for massive field theory? I can understand what it possibly means to exponentiate the dilatation operator in massive theory.
Yeah, so I try to address this a bit at the end. So the dilatation operators, as you mentioned, only defined for massless theories. But this is really about what you're trying to use the renormalization group equations for. And usually, we are using them either when the mass is very light, so negligible, or we are using them for situations where we are such that the mass is very heavy, so we integrate out the particles. Of course, there's an intermediate regime, but this is not the regime where the renormalization group equations are usually used, as this is not the regime where we get large logarithms. So it really depends on which question you are asking, whether this is the right answer for you.
So I should really do your expression as something quantitative, so my sensitivity to theory and to make sense of it. But if I try to use it not quantitatively, I will probably run into this.
I mean, if you're looking at the LHC, I mean, most particles are light. You can just pretty well approximate them with massless particles, but then the top quark, which runs in a triangle to produce the Higgs boson via gluon fusion, that is usually just integrated out. So that is one of the applications in real-world physics where this reasoning would still stand.
I'm not saying that there is an application. I was just wondering if it is a non-quantitative statement or not. It looks like it could not make sense non-quantitatively of such an equation in massive field theory.
Yeah, in this sense I would agree, yeah.